Neptune, the eighth planet from the Sun and the farthest gas giant in our solar system, stands as a testament to the boundless curiosity and ingenuity of humankind. Its discovery in 1846 marked a milestone in astronomical science, as it was the first planet located not by direct observation, but through the application of mathematics. Deviations in the orbit of Uranus led astronomers to predict the existence of another celestial body, whose gravitational influence was altering Uranus's trajectory. This triumph of scientific reasoning, culminating in Johann Galilei's observation, revealed Neptune as a new frontier in our understanding of the cosmos. Named after the Roman god of the sea, Neptune is visually stunning. Its deep blue hue the result of methane in its upper atmosphere absorbing red wavelengths of light. However, its beauty masks an environment of extraordinary extremes. Neptune's atmosphere is composed primarily of hydrogen, helium, and methane, but its defining feature is its tempestuous climate. With winds reaching speeds of up to 300 mph, 2,100 km/h, the planet boasts the strongest winds in the solar system, creating colossal storms and dynamic weather patterns that continue to puzzle and intrigue scientists. Beneath the swirling storms lies a world of even greater mystery. Neptune's internal structure is a layered composition with a gaseous atmosphere transitioning into a thick icy mantle of water, ammonia, and methane, enveloping a solid core made of rock and metal. The core itself reaches temperatures as high as 7,000 degrees Celsius, 12,632 degrees, surpassing the surface heat of the Sun. This intense internal heat, far greater than the amount of energy Neptune receives from the distant Sun, powers the planet's violent weather systems and sustains a magnetic field 27 times stronger than Earth's. In addition to its atmospheric and internal dynamics, Neptune also harbors a fascinating array of rings and moons. Although less prominent than Saturn's iconic rings, Neptune's faint, dark rings are thought to be relatively young and transient, constantly renewed through collisions among its moons and other celestial objects. Triton, Neptune's largest moon, is particularly noteworthy. This icy body, moving in a retrograde orbit, is believed to have been captured by Neptune's gravity, likely originating from the distant Kuiper belt. Triton's surface features active geysers spewing nitrogen gas, making it one of the most geologically active moons in the solar system. Its retrograde motion and dynamic geology hint at a complex and violent past. Despite Neptune's significance in our solar system, it remains largely unexplored. Voyager 2, the only spacecraft to have visited Neptune, provided a brief but invaluable glimpse into the planet's weather patterns and its moons, particularly Triton, during its flyby in 1989. The data and images from this encounter revealed Neptune as a dynamic and active world, with features like the Great Dark Spot, a storm comparable to Jupiter's Great Red Spot, and geysers on Triton. However, with Neptune lying at the far edge of the solar system, nearly 4.5 billion kilometers from the Sun, sending another mission poses significant challenges in terms of time and resources. For now, scientists continue to rely on telescopes, like Hubble and ground-based observatories, to peel back the layers of this enigmatic world. Neptune symbolizes the allure of the unknown. Its distant, icy expanse invites us to venture beyond the familiar, to push the boundaries of what we know and explore the outermost reaches of our cosmic neighborhood. The mysteries of Neptune remind us that, despite our advances, the universe remains a place of wonder, with many secrets still hidden in its vast cold depths. As we continue to unravel the puzzles of this distant planet, Neptune stands as a beacon of the uncharted, encouraging us to keep looking to the stars for answers yet to be found. The story of Neptune is also a story of perseverance and scientific discovery. While Voyager 2 offered humanity its first, and so far only, close-up view of the planet, there is still so much we have yet to understand. Modern technology, despite its leaps, has not fully unlocked Neptune's mysteries. As our telescopes improve and our computational models become more sophisticated, we continue to discover new details about this enigmatic world, offering glimpses into its atmosphere, its storms, and its moons. One of the more exciting prospects for future exploration is the ongoing study of Neptune's magnetic field, which is highly unusual compared to other planets in the solar system. Unlike Earth's magnetic field, which is aligned fairly closely with its rotational axis, Neptune's magnetic field is tilted at an angle of 47 degrees relative to its axis of rotation. Moreover, the magnetic field does not seem to originate from the planet's core, as is the case with Earth, but rather from a shell of electrically conductive fluid that exists within the ice and water layers beneath the atmosphere. This unusual configuration creates a highly dynamic magnetosphere, with shifting magnetic poles that are unlike anything observed elsewhere in the solar system. Understanding Neptune's magnetosphere not only helps us better understand this distant planet, but also gives us insights into magnetic phenomena across the universe. The study of Neptune's moons, particularly Triton, also holds incredible scientific value. Triton, with its retrograde orbit and active surface, continues to challenge scientists' understanding of planetary evolution. Some believe that Triton may harbor a subsurface ocean warmed by tidal forces generated by its odd orbit and internal radioactive decay. Such an ocean could potentially harbor life, much like the suspected oceans beneath the icy crusts of Europa or Enceladus. In this sense, Triton may provide another exciting venue for astrobiological study with the potential to discover life beyond Earth. Even Neptune's atmosphere, with its frigid temperatures and stormy weather, has presented scientists with unexpected findings. One of the most puzzling aspects of Neptune is that it radiates more heat than it absorbs from the Sun. This excess heat drives its massive storms, but the source of this internal energy remains a mystery. Unlike Jupiter and Saturn, which release heat through the slow contraction of their immense atmospheres, a process known as helium rain, Neptune's internal heat source has yet to be definitively identified. Some theories suggest that the dissipation of gravity waves or the convection of fluids deep within the planet may be responsible, but there is no consensus on the mechanism. As the outermost planet, Neptune also serves as a gateway to even more distant regions of the solar system, such as the Kuiper Belt and the Oort cloud. These regions are believed to contain remnants from the early days of the solar system's formation, including icy bodies and dwarf planets like Pluto. Studying Neptune and its interactions with these distant regions can offer clues to the origins of our planetary system. For example, the gravitational influence of Neptune is believed to play a key role in shaping the orbits of many Kuiper Belt objects. And understanding this relationship helps scientists map the distant reaches of the solar system with greater precision. In the broader context of exoplanetary research, Neptune-like planets, or ice giants, are common throughout the universe. Many of the exoplanets discovered to date share similar characteristics with Neptune in terms of size and composition. By studying Neptune in detail, scientists hope to apply their findings to better understand these distant worlds orbiting other stars. Given the rapid advances in exoplanet discovery, particularly with missions like TESS and the James Webb Space Telescope, Neptune has become an important benchmark for interpreting observations of ice giants beyond our solar system. The future of Neptune exploration looks bright, with missions to the outer planets being actively discussed. NASA and other space agencies are considering sending orbiters or probes that would return to Neptune, perhaps even landing on Triton or studying its atmosphere and magnetic field in depth. Such missions, while ambitious and costly, hold the potential to revolutionize our understanding of this distant world and its place in the broader narrative of the solar system's history. Neptune reminds us of the vastness and complexity of space, inviting us to embrace the unknown. Its storms rage on, its moons remain frozen in mystery, and its magnetic field dances in ways we barely comprehend. As we peer deeper into the night sky, Neptune serves as a symbol of our ongoing quest to uncover the secrets of the universe. The questions we ask a day about Neptune's storms, its heat, and its strange magnetic field are the same types of questions that have driven human exploration for centuries. What lies beyond, and how can we understand our place in it? In this cosmic journey, Neptune is not just a distant cold giant, it is a key to unlocking the story of our solar system, a bridge between what we know and what remains to be discovered. It invites us to continue our search for knowledge, to probe the darkest corners of space, and to embrace the challenges that come with exploring the final frontier. Neptune's allure goes beyond its distant location and majestic storms. It represents a chapter in the greater narrative of planetary science, a chapter that is still being written. As the farthest planet in the solar system, Neptune occupies a unique place in our quest to understand the mechanisms that govern planetary formation and evolution. Its status as an ice giant, alongside Uranus, sets it apart from the gas giants Jupiter and Saturn. While all four of these outer planets share characteristics, Neptune's extreme weather, peculiar magnetic field, and distinctive moons demand closer scrutiny. One of the most intriguing questions that continues to challenge scientists is how Neptune and Uranus formed. Their composition, dominated by heavier elements like water, ammonia, and methane, suggests a different formation process than that of the gas giants, which are primarily composed of hydrogen and helium. Theories abound, with some suggesting that Neptune and Uranus formed closer to the Sun before migrating to their current distant orbits. This planetary migration hypothesis has gained traction in recent years, and it fundamentally reshapes our understanding of how planets evolve over time. Neptune, in particular, may have played a significant role in sculpting the solar system, its gravitational influence helping to shape the orbits of smaller objects in the Kuiper belt and beyond. Neptune's distant position has also earned it a special place in the study of the outer solar system. Its proximity to the Kuiper belt has led to a fascinating dance between the planet and these icy remnants of the early solar system. Triton, as mentioned earlier, likely originated in this region before being captured by Neptune's gravity. This possibility makes Triton a relic of the Kuiper belt, an icy time capsule that may contain clues about the formation of the solar system and the conditions in its distant reaches. The capture of Triton also raises the possibility that Neptune has interacted with other large objects in the Kuiper belt, influencing their orbits and even ejecting some from the solar system entirely. This interaction between Neptune and the Kuiper belt provides important context for the study of planetary dynamics. In fact, Neptune's orbit helped astronomers discover the existence of the Kuiper belt itself, as the orbits of some distant objects were found to be influenced by the planet's gravity. The discovery of the Kuiper belt was a groundbreaking moment in astronomy, reshaping our view of the solar system as a more complex and dynamic system. Neptune's role as a cosmic gatekeeper influencing the movement of objects in this distant region further emphasizes its importance in the grand scheme of planetary science. In recent years, with the discovery of numerous exoplanets, Neptune has gained renewed relevance in the search for other planetary systems. Many exoplanets discovered in distant star systems resemble Neptune in size and composition. These Neptune-like planets offer astronomers a valuable point of comparison, allowing them to apply what we've learned from Neptune to these distant worlds. In fact, studying Neptune in greater detail could provide essential insights into the characteristics and atmospheres of exoplanets, especially those that inhabit the outer regions of their own star systems. However, the study of Neptune also comes with significant challenges. Its immense distance from Earth, approximately 30 times farther from the Sun than we are, makes direct exploration difficult and expensive. The Voyager 2 flyby in 1989, which provided the most detailed images and data of Neptune to date, was a fleeting encounter. No mission has returned to Neptune since, leaving many questions unanswered. Yet despite these obstacles, the scientific community continues to push for a dedicated mission to Neptune. Such a mission could focus on exploring Neptune's atmosphere, its complex magnetic field, and its moons, particularly Triton, which remains one of the most intriguing bodies in the solar system. Looking ahead, the next wave of space exploration promises to shed more light on this mysterious planet. The development of advanced propulsion technologies and new spacecraft designs could make a mission to Neptune more feasible in the coming decades. A Neptune orbiter or flyby mission could revolutionize our understanding of this distant world, offering unprecedented insights into its composition, climate, and internal structure. As with all space exploration, the benefits of studying Neptune extend beyond the planet itself, offering broader implications for planetary science, exoplanetary studies, and even our understanding of Earth's own place in the cosmos. Neptune, in many ways, serves as a reminder of how much we have yet to learn. Its deep blue surface, marked by ferocious winds and violent storms, reflects the complexity and unpredictability of the universe. Its rings, thin and elusive, symbolize the fragility and transience of cosmic structures. Triton, orbiting in defiance of the norm, suggests that the universe is full of surprises waiting for us to uncover them. Neptune's magnetic field, with its erratic tilt and shifting poles, challenges our understanding of planetary physics, pushing the boundaries of what we know about magnetic fields across the cosmos. In the grander context of space exploration, Neptune represents a frontier that has yet to be fully explored. It beckons us to push further, to embrace the challenges of distance and time, and to continue the journey of discovery that began centuries ago when humanity first looked up at the stars. The more we learn about Neptune, the more we are reminded of the incredible complexity and beauty of the universe. Neptune's story is far from over, and as we continue to explore its mysteries, we are sure to encounter new revelations that will reshape our understanding of the solar system and our place within it. Neptune, like all of the planets in our solar system, holds the key to understanding the universe at large. Its secrets are bound up with the fundamental questions of science. How did the solar system form? What forces shape the planets? And what lies beyond, in the distant reaches of space? As we look to the future, Neptune serves as a symbol of human curiosity, a reminder that even the most distant and enigmatic worlds are within our reach, if we are willing to take the leap into the unknown. As we continue to contemplate Neptune's mysteries, it becomes clear that this distant giant is more than just a cold, remote world. Its dynamic atmosphere, unique magnetosphere, and intriguing moons present puzzles that challenge the limits of our scientific understanding. Every question we answer about Neptune seems to raise new ones, reminding us of the complexities inherent in studying the cosmos. One of the most tantalizing questions revolves around the planet's internal structure. Unlike the gas giants Jupiter and Saturn, which are composed mostly of hydrogen and helium, Neptune is categorized as an ice giant due to the presence of heavier elements like water, ammonia, and methane. These compounds are present not only in the atmosphere but also in the thick layer beneath it, creating an exotic, icy mantle that surrounds the planet's solid core. Scientists theorize that within this mantle, extreme pressures may cause unusual forms of matter to exist, including superionic water, where water behaves both like a solid and a liquid at the same time. Such a discovery, if confirmed, would deepen our understanding of high-pressure physics and the conditions within ice giants, offering clues about similar planets beyond our solar system. In addition to this intriguing mantle, Neptune's core itself remains a subject of speculation. While we believe it is composed of rock and metal, the exact size, composition, and temperature of the core are still uncertain. Given that Neptune emits significantly more energy than it receives from the Sun, the planet's internal heat must be extraordinary. This internal heat likely contributes to the extreme winds and storms that rage across Neptune's surface, but understanding the precise mechanisms behind these phenomena is a challenge that requires more in-depth exploration. Neptune's powerful winds and dynamic weather patterns continue to captivate scientists. The Great Dark Spot, a massive storm system first observed by Voyager 2, is similar in size and scope to Jupiter's Great Red Spot, although it appears to form and dissipate more rapidly. Hubble observations in recent years have shown that these dark spots appear and disappear over relatively short timescales, suggesting that Neptune's atmosphere is far more volatile than that of the other giant planets. What drives this rapid storm formation? Some scientists propose that Neptune's distance from the Sun may limit solar heating, allowing its internal heat to have a more direct influence on its atmosphere, but the exact relationship between these factors remains unclear. The study of Neptune's storms could provide vital insights into atmospheric dynamics, not only on distant planets but also on Earth and other celestial bodies. Triton, Neptune's largest moon, presents its own unique set of questions. This icy, geologically active moon, with its nitrogen geysers and retrograde orbit, is unlike any other in the solar system. The retrograde motion suggests that Triton was not originally a part of Neptune's system, but was captured by the planet's gravity, likely after forming in the Kuiper belt. If this hypothesis is correct, Triton provides us with a rare opportunity to study a Kuiper belt object up close, offering a window into the early history of the outer solar system. Triton's captured status also raises intriguing possibilities about its internal structure. Could it harbor a subsurface ocean, as some scientists speculate? If so, Triton may join the ranks of other moons, like Europa and Enceladus, that could potentially harbor the conditions necessary for life. The study of Neptune and its moons is also connected to the broader investigation of the Kuiper belt and the objects that reside in this distant region. The Kuiper belt is a vast region beyond Neptune, filled with icy bodies and dwarf planets, remnants of the early solar system. The relationship between Neptune and the Kuiper belt is one of dynamic interaction, with Neptune's gravity shaping the orbits of objects in this region. By studying how Neptune influences the Kuiper belt, scientists hope to gain a better understanding of how planetary systems evolve over time and how gravitational interactions can shape the architecture of such systems. Moreover, Neptune's place in the wider context of planetary science extends beyond our solar system. Many exoplanets discovered around distant stars are classified as Neptune-like due to their size and composition. These ice giant exoplanets share characteristics with Neptune and Uranus, offering us an opportunity to compare our findings at home with observations of distant worlds. Understanding Neptune's atmosphere, magnetic field, and internal structure can provide valuable models for interpreting data from these exoplanets, helping scientists assess their potential habitability, climate dynamics, and evolutionary histories. While much of our knowledge of Neptune has come from telescopic observations and data gathered by Voyager 2, the future of Neptune exploration holds incredible promise. With advances in technology, including the potential for new missions to the outer solar system, we stand on the cusp of another era of discovery. Proposals for future space missions, such as Neptune orbiters or even flyby missions to Triton, have the potential to revolutionize our understanding of this distant world. A Neptune orbiter, for instance, could map the planet's magnetic field in greater detail, probe its atmosphere, and study its moons, providing answers to many of the questions left by Voyager 2's brief encounter. Another area of exploration that is gaining attention is the study of Neptune's rings. Though not as prominent as Saturn's, Neptune's rings are a fascinating part of its system. These thin, dark rings are thought to be relatively young and constantly replenished by debris from moons or comets. Understanding the origin and evolution of these rings can offer insights into the processes that shape planetary ring systems both in our solar system and beyond. Additionally, studying how Neptune's gravity interacts with these rings and nearby moons could reveal new details about the planet's gravitational field and its influence on surrounding objects. With its deep blue atmosphere, violent winds, and icy moons, represents a cosmic frontier that beckons exploration. It stands as a symbol of both how far we have come in understanding our solar system and how much remains to be discovered. Each mystery that Neptune presents brings with it new opportunities for scientific inquiry, challenging us to push the boundaries of what we know. As we continue to refine our instruments, launch new missions, and develop more sophisticated models, Neptune will remain a key target for scientific discovery. Its secrets, locked away in the icy depths of the outer solar system, are waiting to be uncovered. And just as the mathematical predictions of the 19th century led to Neptune's discovery, the future promises to unveil even more about this distant, enigmatic world. Neptune, as the furthest major planet in our solar system, occupies a special place in both our scientific endeavors and in the broader narrative of exploration. It stands as a reminder that, even at the limits of our immediate cosmic neighborhood, the universe holds extraordinary secrets. For centuries, humanity's quest to understand these mysteries has driven technological innovation, expanded our intellectual horizons, and connected us more deeply to the cosmos. Neptune is a symbol of this relentless pursuit, embodying the spirit of exploration that pushes us ever forward. One of the most captivating aspects of Neptune is the sheer scale of its storms. The Great Dark Spot, first observed during the Voyager 2 flyby, was an immense storm system similar in size to Earth itself, although it dissipated within a matter of years. More recent observations from the Hubble Space Telescope have revealed that new dark spots continue to form and vanish, a process that remains difficult to fully explain. These storms, which often span thousands of kilometers, suggest a highly dynamic atmosphere where forces far beyond our understanding are at play. The persistence of such immense storms is indicative of Neptune's intense internal energy, driven by the mysterious heat source that allows it to radiate more energy than it receives from the Sun. Exploring these atmospheric phenomena could yield insights not only about Neptune, but also about the complex interplay between planetary atmospheres and internal energy sources, knowledge that could be applicable to many other worlds, both in and outside our solar system. Neptune's peculiar magnetic field adds another layer to its complexity. Unlike Earth's relatively stable magnetic field, Neptune's is highly tilted and offset from its center, leading to dramatic variations in strength across the planet. This misalignment is thought to be generated by the movement of conductive fluids within the planet's outer layers, rather than the core, as is the case with Earth. The study of Neptune's magnetosphere could provide key insights into how magnetic fields are generated in ice giants, an area of planetary science that is still not fully understood. Understanding these dynamics is not just important for understanding Neptune itself, but for drawing broader conclusions about planetary magnetic fields across the cosmos. Many exoplanets, including those similar in size and composition to Neptune, likely possess magnetic fields, and by studying Neptune's unique case, we can refine our models for these distant worlds. Beyond its individual characteristics, Neptune plays a critical role in the context of planetary formation and migration. Modern theories of planetary development suggest that Neptune and its sibling Uranus formed closer to the Sun before migrating outward to their current orbits. This idea is part of the Nice model, named after the French city where it was developed, which proposes that the early solar system was far more chaotic than it is today. According to this model, Neptune and Uranus may have swapped positions or even interacted with Jupiter and Saturn in a way that scattered other planetesimals and small bodies into the Kuiper belt and beyond. These interactions likely played a significant role in shaping the architecture of the outer solar system, contributing to the distribution of dwarf planets, comets, and other objects we observe today. The capture of Triton by Neptune may also be a consequence of this early period of planetary migration. Triton's retrograde orbit and unusual geological activity indicate a violent past, suggesting that it was once an independent body, possibly a dwarf planet similar to Pluto, that was drawn into Neptune's gravitational influence. If this is the case, Triton represents a rare opportunity to study a Kuiper belt object up close without sending a mission to the distant reaches of the solar system. Its nitrogen geysers and relatively young surface, with few impact craters, make it one of the most active moons in the solar system and a prime target for future missions. Exploring Triton could provide key insights into how icy bodies evolve and whether they could harbor subsurface oceans, a topic of great interest in the search for extraterrestrial life. Triton's potential to host a subsurface ocean beneath its icy shell raises profound questions about the habitability of moons in the outer solar system. While traditionally we have focused on planets when searching for life, recent discoveries, such as Europa's likely ocean and Enceladus water plumes, suggest that moons may offer some of the most promising environments for life beyond Earth. Triton, with its unique history and retrograde orbit, could provide valuable data to support this growing body of research. If future missions to Triton confirm the presence of an ocean, it could redefine the boundaries of where we search for life in the universe. The distant Kuiper belt, extending beyond Neptune's orbit, is home to thousands of icy objects, many of which may have been influenced by Neptune's gravity. By studying how Neptune has shaped the orbits of these bodies, scientists can gain a better understanding of the early dynamics of the solar system. The discoveries made in this region, such as those by the New Horizons mission, which flew past Pluto in 2015, have shown us that the outer solar system is far more complex than previously thought. Neptune, with its gravitational influence extending into this distant realm, serves as a crucial key in unlocking the history and evolution of these outermost regions. In addition to advancing our understanding of our own solar system, Neptune holds special relevance for the study of exoplanets. Many of the exoplanets discovered to date are classified as ice giants similar in size and composition to Neptune. These Neptunes orbit stars at a range of distances, offering astronomers the opportunity to compare the characteristics of distant worlds with our own. By continuing to study Neptune, we gain a comparative framework that helps us interpret the atmospheric, magnetic, and geological features of exoplanets. This comparative planetology allows us to refine our models of planetary evolution and assess the habitability potential of distant worlds. Looking ahead, the future of Neptune exploration is full of exciting possibilities. NASA's upcoming missions, such as the James Webb Space Telescope and the development of more advanced spacecraft, offer the potential to revolutionize our understanding of Neptune and the outer solar system. One proposed mission, the Neptune Odyssey, would send an orbiter to study Neptune in detail, with a focus on its atmosphere, magnetic field, and moons. Such a mission would give scientists the opportunity to conduct long-term observations of Neptune's weather patterns, magnetic field shifts, and ring dynamics. Additionally, future missions to Triton could provide direct evidence of subsurface oceans or reveal new geological processes that could further illuminate the mysteries of icy moons. In the end, Neptune is not just a distant world on the edge of our solar system. It is a gateway to understanding the outer reaches of the universe. Its mysteries invite us to keep exploring, to keep asking questions about how our planetary system formed, evolved, and continues to change. As we send new missions into space and develop more sophisticated tools for observation, Neptune will remain an object of fascination and discovery, reminding us that the journey of exploration is far from over. Neptune's allure lies in the questions it poses and the discoveries it promises. From its wind-swept clouds to its icy moons, from its dynamic magnetosphere to the distant reaches of the Kuiper belt, Neptune embodies the frontier spirit of science. It encourages us to look beyond the known and to venture into the vast, cold expanse of space with curiosity and wonder, ever seeking to unlock the secrets of the universe. Neptune, with all its complexities and mysteries, represents more than just a distant planet. It embodies the very essence of the scientific quest for knowledge. Its position on the fringes of the solar system, over 4.5 billion kilometers from the Sun, makes it an elusive target for exploration, but one that holds tremendous potential to unlock some of the most profound questions we have about planetary systems, both in our cosmic neighborhood and beyond. As technology advances, the desire to return to Neptune and further investigate its many peculiarities grows stronger. The single flyby by Voyager 2 in 1989, while groundbreaking at the time, left scientists hungry for more. Voyager's brief encounter revealed Neptune as a dynamic and active planet, but much was left unexplored. The tantalizing hints provided by its images and data sparked questions that have only intensified over the decades. Since then, no mission has revisited Neptune, but the possibility of future expeditions opens up a new horizon of discovery. One of the most exciting potential missions is the idea of sending an orbiter to Neptune, a project that has gained interest among planetary scientists. A Neptune orbiter would allow for prolonged observation of the planet's atmosphere, magnetic field, and its moons, particularly Triton. Such a mission would be a monumental step in planetary science, enabling us to gather data over a longer period, rather than the brief snapshot provided by flyby missions. By monitoring Neptune's atmosphere over time, we could better understand its violent storms, the mechanisms behind its supersonic winds, and the processes driving its atmospheric dynamics. Long-term observations could also reveal how Neptune's great dark spots form and disappear, offering insights into storm systems both on Neptune and potentially on exoplanets with similar characteristics. Studying Neptune's magnetosphere in greater detail could provide answers to long-standing questions about the planet's internal structure and its magnetic field generation. The tilt and offset of Neptune's magnetic field remain largely unexplained, but a dedicated mission could map its magnetic field with unprecedented precision, helping us understand how ice giants generate their magnetic fields. The data gathered could also shed light on the behavior of magnetic fields on other planets, including Earth, as well as exoplanets in distant star systems. Another compelling target for future missions is Triton, Neptune's largest moon. Voyager 2's brief observations of Triton revealed a world unlike any other, with active nitrogen geysers and a young, geologically active surface. Triton's retrograde orbit suggests that it was once a Kuiper belt object, captured by Neptune's gravity billions of years ago. If this is true, Triton could offer a unique glimpse into the distant past of the solar system. Moreover, some scientists speculate that Triton may harbor a subsurface ocean beneath its icy crust, warmed by tidal forces generated by its unusual orbit. If confirmed, such an ocean would make Triton one of the most promising places to search for life in the outer solar system, adding it to the growing list of moons with astrobiological potential, alongside Europa, Enceladus, and Titan. The possibility of a mission to land on Triton, or even to probe beneath its surface, would mark a monumental achievement in space exploration. Such a mission could explore the moon's surface in detail, study its geysers up close, and perhaps even drill through its icy crust to search for signs of life in the liquid water below. The scientific payoff of such a mission would be enormous, offering unparalleled insights into the geological processes that shape icy moons, as well as the potential for life in extreme environments far from the warmth of the Sun. Beyond Neptune's immediate system, its interaction with the Kuiper belt and the Oort cloud presents another frontier of exploration. Neptune's gravity has shaped the orbits of many objects in these distant regions, providing clues about the early history of the solar system. The Kuiper belt, home to dwarf planets like Pluto and countless smaller icy bodies, represents the remnants of the primordial solar system. Studying Neptune's role in sculpting this region could reveal how planets migrate and interact with their surroundings, shedding light on similar processes occurring in exoplanetary systems across the galaxy. In fact, Neptune's importance extends far beyond the solar system. As we continue to discover exoplanets in other star systems, many of these planets bear a striking resemblance to Neptune. Ice giants, like Neptune and Uranus, appear to be common in the universe, and by studying Neptune in detail, we can gain valuable insights into the behavior, formation, and atmospheric dynamics of these distant worlds. Exoplanetary research is one of the most rapidly growing fields in astronomy, and Neptune provides a critical benchmark for interpreting the data we gather from exoplanets. In recent years, instruments like the James Webb Space Telescope and the Transiting Exoplanet Survey satellite tests have revolutionized our ability to study distant planets. By comparing the atmospheres of Neptune-like exoplanets with that of Neptune itself, scientists can refine their models of how these planets form and evolve. The discovery of exoplanets in the habitable zones of their stars, where conditions may be suitable for liquid water, has also raised the possibility of finding Neptune-like planets with conditions that could support life. Understanding how Neptune's atmosphere and internal dynamics work could help scientists assess the potential habitability of ice giants orbiting distant stars. As we stand on the brink of a new era of space exploration, Neptune beckons us to return. It represents a frontier of scientific discovery, where the answers to fundamental questions about planetary formation, atmospheric dynamics, and the potential for life in the universe await. The challenges of reaching Neptune are great, but the rewards are even greater. The advancements made in propulsion technology, spacecraft design, and observational tools bring us closer to making these missions a reality. Neptune, with its deep blue clouds and violent storms, remains a symbol of the unknown, a reminder of how much there is left to discover in our own solar system, let alone in the wider universe. It is a world shaped by forces we barely understand, planets on the edge of our cosmic reach, but within our grasp as we continue to push the boundaries of exploration. In the end, the study of Neptune is not just about understanding a distant planet, it's about expanding the horizons of human knowledge. As we uncover the secrets of Neptune, we gain a deeper understanding of the forces that have shaped our own world, the planets around us, and the cosmos as a whole. Neptune's mysteries challenge us to think bigger, to ask bold questions, and to seek answers in the farthest reaches of space. And as we embark on the next phase of this journey, Neptune will continue to be a guiding light, leading us further into the unknown, where new discoveries await. As we continue our exploration of Neptune, it is essential to recognize the broader implications of studying this distant planet. While Neptune might seem isolated at the edge of the solar system, its relevance extends far beyond its immediate surroundings. By probing deeper into Neptune's mysteries, we not only advance our understanding of this enigmatic world, but also enhance our knowledge of planetary systems, cosmic evolution, and even the potential for life in extreme environments. Neptune's dynamic atmosphere remains one of its most striking features. The violent storms and supersonic winds that define its climate challenge our understanding of atmospheric dynamics. Unlike Earth, where weather systems are driven by the sun's energy, Neptune is so far from the sun that it receives only a fraction of the solar energy compared to planets like Earth or Venus. Yet despite this, Neptune's atmosphere is far from calm. The planet's internal heat, radiating from deep within, powers these dramatic storms, making Neptune a laboratory for studying how atmospheres can behave under different energy inputs. The Great Dark Spot, first observed by Voyager 2, provides a fascinating case study in planetary weather systems. These massive storm systems form and dissipate with relative speed, indicating that Neptune's atmosphere is in constant flux. Hubble observations since Voyager's flyby have shown new dark spots emerging, revealing that Neptune's atmospheric conditions are far more changeable than originally thought. These rapid changes challenge our models of storm formation and provide crucial data for understanding how atmospheres on other planets, including exoplanets, might behave. Exoplanetary atmospheres, particularly those on planets similar in size and composition to Neptune, may experience similar phenomena, and studying Neptune helps refine our predictions for those distant worlds. One of the most intriguing aspects of Neptune's storms is their longevity. While storms on Earth may last for days or weeks, Neptune's storms can persist for years before finally dissipating. These massive systems, spanning thousands of kilometers, highlight the enormous energy circulating within Neptune's atmosphere. Understanding the drivers behind these long-lived storm systems could offer new insights into atmospheric science, including the forces that sustain such storms. This knowledge may also be transferable to studying weather patterns on gas giants and ice giants in exoplanetary systems, where we lack the ability to make direct observations. Beyond its atmosphere, Neptune's magnetosphere continues to puzzle scientists. As previously noted, its magnetic field is highly tilted relative to its axis and significantly offset from the planet's core. The magnetic field also shifts dramatically over time, leading to a highly dynamic magnetosphere that likely interacts in complex ways with the planet's atmosphere and moons. This erratic magnetic field, believed to be generated by the movement of electrically conductive fluids in Neptune's icy mantle, offers a rare glimpse into the workings of planetary magnetic fields that deviate from the more stable model seen on Earth or Jupiter. Studying Neptune's magnetosphere could also have important implications for understanding exoplanetary systems. Many exoplanets, particularly ice giants like Neptune, are thought to have similarly complex magnetic fields, and by studying Neptune in detail, scientists can develop better models for these distant worlds. Magnetic fields play a crucial role in planetary habitability, as they shield planets from cosmic and solar radiation, protecting their atmospheres and, potentially, any life that might exist. By understanding Neptune's magnetic field, we can better assess how magnetic fields on exoplanets might influence their atmospheres and the potential for life to thrive in such environments. Neptune's moons, particularly Triton, present another fascinating avenue of exploration. As one of the few geologically active moons in the solar system, Triton's retrograde orbit and nitrogen geysers point to a history of dramatic change. The fact that Triton orbits Neptune in the opposite direction to the planet's rotation suggests that it was captured by Neptune's gravity, likely after forming elsewhere in the Kuiper belt. This makes Triton a rare opportunity to study a captured object from the Kuiper belt, a region of space filled with icy bodies that represent the remnants of the early solar system. Triton's geologic activity, despite its frigid surface temperatures, hints at internal heat sources that may still be active today. Some scientists believe that tidal forces generated by Triton's orbit around Neptune may cause internal friction, keeping the moon's interior warm enough to support a subsurface ocean. If this is the case, Triton joins the ranks of other moons like Europa and Enceladus, where subsurface oceans may harbor the conditions necessary for life. A mission to Triton could confirm the presence of this ocean, providing valuable data on the potential for life in extreme environments far from the sun's warmth. The possibility of finding life on Triton or on other icy moons raises profound questions about the nature of life itself. Traditionally, our search for life has focused on planets in the habitable zone, where liquid water can exist on the surface. However, the discovery of subsurface oceans on moons like Triton, Europa, and Enceladus suggests that life might exist in environments far beyond the traditional habitable zone. These icy moons may provide environments where microbial life could thrive, protected from the harsh conditions of space by thick ice shells. The discovery of such life would revolutionize our understanding of biology and expand the potential habitats where life could exist in the universe. Neptune's relationship with the Kuiper belt is another key area of study that holds the potential to reshape our understanding of planetary formation and migration. As the outermost planet, Neptune exerts a significant gravitational influence on the objects in the Kuiper belt, helping to shape their orbits. The Kuiper belt itself is a region filled with icy bodies, including dwarf planets, like Pluto, that formed during the early stages of the solar system. By studying how Neptune interacts with these objects, scientists can gain insights into the forces that governed the early solar system's evolution and how planets like Neptune migrated to their current positions. The Kuiper belt is also believed to be a source of short-period comets which periodically enter the inner solar system. Neptune's gravity likely plays a role in sending these comets on their long journeys toward the Sun. Studying Neptune's gravitational influence on the Kuiper belt can help us understand the mechanisms that send comets hurtling into the inner solar system, where they may have played a role in delivering water and organic molecules to Earth during its early history. In the context of exoplanetary research, Neptune remains a critical reference point. Ice giants like Neptune are common in other star systems, and studying our own ice giant provides a valuable baseline for interpreting observations of exoplanets. Many of the exoplanets discovered to date are classified as Neptunes, and by understanding Neptune's atmosphere, magnetic field, and internal structure, we can make better predictions about the behavior of similar planets orbiting distant stars. The James Webb Space Telescope, with its advanced capabilities, is expected to provide unprecedented data on exoplanetary atmospheres, allowing us to compare distant ice giants to Neptune. Looking ahead, the future of Neptune exploration is filled with potential. New spacecraft missions, advanced telescopes, and improved computational models will continue to push the boundaries of our knowledge. Neptune, with its violent storms, complex magnetic field, and icy moons, offers a wealth of opportunities for discovery. As we continue to unravel the mysteries of this distant planet, we not only learn more about our own solar system, but also gain valuable insights into the nature of planetary systems across the universe. Neptune stands as a symbol of our unending quest for knowledge. Its secrets, locked away in the cold depths of space, remind us that there is still so much we do not know. But with each new mission, each new observation, we come closer to understanding this distant world and our place in the cosmos. The study of Neptune is not just about one planet. It is about exploring the very limits of human curiosity and pushing the frontiers of science ever further into the unknown. Neptune's mysteries are part of a broad narrative that connects us to the grander workings of the cosmos. As the most distant of the major planets in our solar system, it serves as a portal to the outer regions, where the rules governing planetary formation, migration, and evolution are still being written. Each step toward understanding Neptune brings us closer to comprehending not only the intricacies of our own planetary neighborhood, but also the fundamental processes that shape planets across the universe. One of the critical areas where Neptune plays a leading role is in the study of planetary migration. As scientists develop more sophisticated models of how the solar system evolved, it becomes increasingly clear that the planets did not always reside in their current positions. Early in the history of the solar system, gravitational interactions between the giant planets caused a period of intense instability, resulting in the migration of these planets from their original orbits. This nice model, named after the city where it was first developed, suggests that Neptune was originally much closer to the Sun and that its migration outward played a pivotal role in reshaping the solar system. During this migration, Neptune likely scattered countless smaller bodies into distant orbits, forming the Kuiper Belt, and contributing to the Oort cloud, a vast region of icy bodies far beyond Pluto. Some of these scattered objects may have been captured by Neptune, such as Triton, while others were ejected entirely from the solar system. Understanding Neptune's role in this cosmic reshuffling provides critical insights into how planetary systems evolve over time. Such knowledge is essential for interpreting the dynamics of exoplanetary systems, many of which show evidence of planetary migration, often with planets in unexpected orbits or configurations. Neptune's migration likely had a profound impact on the architecture of the Kuiper Belt, a region that has only recently come into sharper focus thanks to missions like New Horizons, which provided the first close-up images of Pluto and its moons. The Kuiper Belt is believed to contain the remnants of the early solar system, objects that have remained relatively unchanged for billions of years. By studying Neptune's influence on the Kuiper Belt, we can learn more about the forces that shape the outer regions of the solar system and how similar belts of debris might form around other stars. Triton, Neptune's largest moon, remains one of the most compelling clues to Neptune's early history. Captured by Neptune's gravity billions of years ago, Triton offers a unique window into the Kuiper Belt's past. Its retrograde orbit and active surface suggest a complex and violent history. But what makes Triton even more intriguing is the possibility that it may harbor a subsurface ocean beneath its icy shell. If confirmed, this would make Triton a prime candidate for the search for extraterrestrial life. The discovery of life in such an environment would revolutionize our understanding of biology, suggesting that life could exist in many more places throughout the cosmos than previously thought. This possibility has led to calls for future missions to Triton, and indeed, it remains one of the most sought-after targets for planetary exploration. A lander or orbiter mission to Triton could probe its icy surface, study its nitrogen geysers, and potentially detect signs of a hidden ocean. With advances in robotic exploration and the potential for new technologies such as nuclear-powered spacecraft, missions to Neptune and Triton could become a reality in the coming decades. These missions would not only provide critical data about Neptune's atmosphere, magnetosphere, and moons, but also push the boundaries of exploration to the very edges of the solar system. The importance of studying Neptune extends beyond its role within our solar system. Neptune is the archetype of an ice giant, a type of planet that appears to be common throughout the universe. Many of the exoplanets discovered in recent years fall into this category, and Neptune serves as a crucial reference point for understanding their atmospheric composition, magnetic fields, and internal structures. By studying Neptune in detail, we gain the ability to interpret data from exoplanetary systems, helping us understand how these distant worlds formed, evolved, and what their atmospheres might be like. The potential for habitability on exoplanets is also deeply tied to our understanding of planets like Neptune. While the gas giants and ice giants in our own solar system are inhospitable to life as we know it, their moons could provide viable environments for life. Europa and Enceladus, moons of Jupiter and Saturn, are already prime candidates for the search for extraterrestrial life due to their subsurface oceans, and Triton could soon join this list. As we continue to discover exoplanets in the habitable zones of distant stars, many of these systems may contain Neptune-like planets with moons that harbor liquid water beneath their icy shells. Studying Neptune and its moons helps us refine our search for life in these distant systems. As humanity looks toward the next phase of space exploration, Neptune offers an unparalleled opportunity to test new technologies and push the limits of our reach. The development of more advanced propulsion systems, such as ion thrusters or nuclear propulsion, will be crucial for future missions to Neptune given its distance from Earth. These missions will likely take decades to plan and execute, but the scientific rewards will be immense. Understanding the structure of Neptune's atmosphere, mapping its magnetic field in detail, and exploring its moons would open new chapters in our knowledge of the outer solar system. In many ways, Neptune represents the future of planetary science. It challenges us to think bigger, to explore further, and to develop new ways of understanding the universe. The planet itself is a reminder of how much we have yet to discover, not just in the distant reaches of our solar system, but across the galaxy. Each new piece of data we gather about Neptune brings us one step closer to answering the profound questions that have driven human curiosity for centuries. How did the solar system form? What forces shape the planets and moons we see today, and what lies beyond in the vast unknown? As the exploration of Neptune continues, it will undoubtedly reveal more surprises. Its storms, its magnetic field, its captured moon Triton, and its interactions with the Kuiper Belt will all provide valuable clues to understanding the processes that govern the solar system. But perhaps most importantly, Neptune reminds us that exploration is not just about reaching new destinations, it's about expanding the boundaries of what we know and pushing forward into the unknown. The mysteries of Neptune are vast, but so is the potential for discovery. As we peer deeper into the cosmos and send new missions to explore the outer planets, Neptune will remain a symbol of our enduring quest to understand the universe. In the years and decades to come, it will inspire new generations of scientists, engineers, and explorers to take on the challenge of the unknown, continuing humanity's journey to the stars. Neptune's exploration marks the beginning of a new era in humanity's relationship with the outer solar system. It stands not just as an isolated entity, but as part of a larger narrative that stretches from the early formation of the solar system to the far reaches of interstellar space. Every discovery about Neptune brings us closer to understanding how planetary systems evolve and how the various celestial bodies interact to create the complex, dynamic environments we observe today. One of the most profound aspects of Neptune's study is how it forces us to reevaluate the processes of planetary formation. Traditional models once envisioned the solar system as a relatively static environment, with planets forming and remaining in fixed orbits. However, with the development of more advanced theories, particularly the Nice model, it is now understood that the early solar system was far more chaotic than previously imagined. Giant planets like Neptune and Uranus likely migrated outward, disturbing vast numbers of smaller objects and reshaping the entire solar system in the process. This planetary migration is thought to have led to the scattering of countless icy bodies into distant orbits, creating regions like the Kuiper Belt and the Oort cloud. These regions are the remnants of the solar system's formative years, holding clues about the processes that shaped the planets and moons we observe today. Neptune's migration outward also likely played a significant role in shaping the orbits of these objects, and by studying Neptune's influence on them, we can gain insights into how other planetary systems might behave. The discovery of similar belts of debris around other stars suggests that these processes are not unique to our solar system, making Neptune a key player in understanding the architecture of planetary systems across the universe. The Kuiper Belt, in particular, is a region rich with scientific potential, home to countless small icy bodies, including dwarf planets like Pluto. It represents a relatively untouched region of the solar system where objects have remained frozen in time for billions of years. By studying Neptune's gravitational influence on these objects, scientists can unravel the history of the solar system's outer reaches and explore the conditions that existed during its earlier stages. This knowledge could also provide valuable context for understanding similar belts of debris around distant stars, helping us to interpret the data we gather from exoplanetary systems. Neptune's relationship with Triton, its largest moon, adds yet another layer of complexity to this story. Triton, captured by Neptune's gravity billions of years ago, is believed to have once been a part of the Kuiper belt. This makes it a unique case study, a Kuiper belt object that has been brought into the inner system of a gas giant, offering a rare opportunity to study the characteristics of such objects up close. Triton's retrograde orbit and geologic activity provide compelling evidence that it has undergone significant changes since its capture, and its current state may hold important clues about how gravitational interactions between planets and moons can reshape entire worlds. In many ways, Triton is a key to understanding the early history of the solar system and the processes that govern the capture of celestial bodies. By studying Triton in greater detail, scientists hope to learn more about how Neptune's migration influenced the formation of the Kuiper belt, and how similar processes might play out in other planetary systems. Triton's active surface, with its nitrogen geysers and relatively young terrain, also makes it an exciting target for astrobiology. The possibility that Triton harbors a subsurface ocean beneath its icy crust adds a new dimension to the search for life in the outer solar system. If liquid water exists beneath Triton's surface, it could provide the conditions necessary for life, much like the subsurface ocean suspected on Europa and Enceladus. The prospect of a mission to Triton, or even a dedicated Neptune orbiter, is becoming increasingly attractive to the scientific community. Such a mission could provide long-term observations of Neptune's atmosphere, magnetosphere, and moons, offering unprecedented insights into this distant world. An orbiter could monitor Neptune's violent weather systems, study its shifting magnetic field, and probe the interactions between Neptune's rings and its moons. Meanwhile, a lander or probe to Triton could explore the moon's surface and potentially drill beneath the ice to search for evidence of the subsurface ocean. Such missions would be challenging, given the vast distances involved, but the scientific payoff would be immense. In the broader context of planetary science, Neptune also serves as a critical reference point for studying ice giants in other star systems. Many of the exoplanets discovered to date fall into the category of Neptune-like planets, ice giants that share similar characteristics in terms of size and composition. These planets often orbit their stars at distances where liquid water is unlikely to exist on the surface, but they may possess moons or subsurface oceans that could provide environments conducive to life. By studying Neptune and its moons in detail, scientists can develop better models for interpreting the data we gather from exoplanetary systems, helping us assess their habitability and the potential for finding life beyond Earth. Neptune's importance extends beyond the search for life. The planet's dynamic atmosphere, with its powerful storms and supersonic winds, offers a unique opportunity to study atmospheric dynamics under extreme conditions. Unlike Earth, where solar heating drives weather systems, Neptune's weather is powered primarily by its internal heat. This heat, radiating from deep within the planet, fuels immense storm systems that rage across the planet's surface. Understanding how these storms form and persist could provide valuable insights into the behavior of atmospheres on other planets, both in our solar system and in distant star systems. Neptune's internal heat is another mystery that has yet to be fully explained. The planet emits more heat than it receives from the sun, suggesting that there are powerful processes at work deep within its interior. Some theories propose that Neptune's internal heat is generated by the slow compression of its atmosphere, while others suggest that the dissipation of gravity waves may play a role. Whatever the mechanism, it is clear that Neptune's internal heat is a driving force behind its violent weather, and understanding this heat source could provide new insights into the behavior of ice giants throughout the universe. As we continue to study Neptune, we are reminded of the broader implications of planetary exploration. Every discovery about Neptune not only enhances our understanding of the solar system but also contributes to our knowledge of planetary systems across the galaxy. Neptune's role in the migration of planets, its interactions with the Kuiper belt, and its dynamic atmosphere offer clues about the processes that shape planetary systems everywhere. The data we gather from Neptune will inform our models of exoplanets, helping us to interpret the observations we make with telescopes like the James Webb Space Telescope and future missions that will probe even deeper into the cosmos. Neptune, with its deep blue clouds and distant position at the edge of the solar system, symbolizes the vastness of what we have yet to explore. It reminds us that even in our own cosmic neighborhood, there are still many unknowns, many mysteries waiting to be solved. As we develop new technologies and embark on more ambitious missions, Neptune will remain a key destination for exploration, representing the outer limits of our understanding and the next great frontier in planetary science. In the coming decades, humanity's exploration of Neptune will likely yield discoveries that reshape our view of the solar system and the universe. Its storms will continue to rage, its moons will continue to intrigue, and its secrets will beckon us to delve deeper. The journey to understand Neptune is far from over. It is just beginning, and with each new mission, we come closer to unraveling the mysteries of this distant world and its place in the cosmos. Neptune's story is not just about a single planet. It is about the evolution of planetary science and our capacity to explore the farthest reaches of our solar system. Each mission, observation, and theory builds on centuries of human curiosity, stretching back to the early days of astronomy when Neptune's existence was first predicted by mathematics, rather than direct observation. This achievement alone symbolizes the power of human intellect to reach beyond immediate perception, applying abstract principles to uncover hidden truths about the universe. As we continue our study of Neptune, the planet's potential to reshape our understanding of the outer solar system and planetary systems as a whole grows ever more evident. One of the most exciting aspects of Neptune's exploration is the possibility of finding answers to fundamental questions about how our solar system, and others, came to be. Neptune plays a crucial role in the narrative of planetary formation and migration, having influenced the trajectories of countless objects during its outward journey from the inner solar system. The early solar system was a place of immense chaos and instability, with gravitational forces pushing and pulling planets and smaller bodies into new orbits. As Neptune migrated outward, it is believed to have swept up and scattered countless planetesimals, sending many into the Kuiper belt or ejecting them from the solar system entirely. This period of dynamism is crucial to understanding why the solar system looks the way it does today, with the giant planets positioned far from the Sun and the Kuiper belt and Oort cloud populated by a vast array of icy objects. This process of planetary migration is not unique to our solar system. Evidence from exoplanetary studies suggests that migration is a common feature of planetary systems throughout the galaxy. Many exoplanets have been found in orbits that challenge traditional models of planet formation, with some gas giants located extremely close to their parent stars in orbits far too tight for them to have formed there. By studying how Neptune's migration influenced the outer solar system, we can draw parallels to the migration patterns observed in exoplanetary systems, helping us to refine our models of planetary evolution on a universal scale. One of the most striking discoveries in recent years is the sheer number of Neptune-like exoplanets. These ice giants, similar in size and composition to Neptune, appear to be a common outcome of planetary formation. Many of these planets are located in the so-called Neptune Desert, a region close to their parent stars where such large planets were not expected to be found. These discoveries challenge our understanding of how planets form and migrate, suggesting that the processes governing planetary formation are far more complex than previously thought. By studying Neptune in detail, we can begin to piece together the puzzle of how ice giants form, migrate, and interact with other planets and debris in their systems. Moreover, Neptune's status as an ice giant makes it a key point of comparison for understanding the atmospheric dynamics of exoplanets. Ice giants have thick atmospheres composed of hydrogen, helium, and various ices, like water, ammonia, and methane. Neptune's distinct deep blue color is the result of methane in its upper atmosphere, which absorbs red light and reflects blue. Understanding how these atmospheric components interact with internal heat and external solar radiation provides a template for interpreting the atmospheres of exoplanets, many of which exhibit similar characteristics. By analyzing the wind, storms, and thermal structure of Neptune's atmosphere, we can gain insights into the weather patterns and climate systems on distant worlds. The mysteries of Neptune's interior are another area of active research that holds implications for both our solar system and the study of exoplanets. Beneath Neptune's turbulent atmosphere lies a vast mantle of water, ammonia, and methane compressed into exotic forms under immense pressure. Some models suggest that deep within Neptune these materials could exist in a supersonic state, where water behaves both like a solid and a liquid simultaneously, with oxygen ions locked in a lattice and hydrogen ions freely flowing through it. Understanding how these materials behave under extreme pressure could revolutionize our knowledge of planetary interiors, particularly for ice giants in other star systems. The internal structure of Neptune may also provide clues to the planet's magnetic field, which is generated by the movement of electrically conductive materials within its mantle. Neptune's magnetic field itself is a puzzle that demands further investigation. Unlike Earth's magnetic field, which is relatively well aligned with its rotational axis, Neptune's magnetic field is highly tilted and offset from the planet's center. This unusual configuration leads to complex interactions between the planet's magnetosphere and its atmosphere, as well as with its moons. Mapping Neptune's magnetic field in greater detail would provide critical insights into how magnetic fields are generated in ice giants and how they influence the behavior of charged particles in the planet's magnetosphere. These findings could then be applied to understanding magnetic fields on exoplanets, many of which are likely to possess similarly complex magnetic environments. Triton, Neptune's largest moon, remains one of the most compelling targets for future exploration, not just because of its geological activity, but also because of its origins as a captured object from the Kuiper Belt. Triton offers a rare opportunity to study a Kuiper Belt object up close, providing insights into the early history of the solar system and the processes that shaped the outer regions. Its retrograde orbit suggests that Triton was once a dwarf planet, similar to Pluto, before being captured by Neptune's gravity. This capture likely caused significant tidal heating, which may have contributed to Triton's geologic activity. Triton's nitrogen geysers, observed by Voyager 2, are a testament to this ongoing activity, suggesting that the moon's interior is far more dynamic than previously thought. The possibility of a subsurface ocean on Triton adds a new layer of intrigue to the search for life in the outer solar system. If such an ocean exists, it could provide the necessary conditions for life to exist, protected from the harsh environment of space by the moon's icy shell. The discovery of life on Triton, or any other icy moon, would have profound implications for astrobiology, expanding the range of environments where life could potentially thrive. A mission to Triton could also help us understand the processes that govern the evolution of icy bodies and how they interact with their parent planets, offering a new perspective on the diversity of planetary systems. In the grand scheme of space exploration, Neptune represents both a challenge and an opportunity. Its immense distance from Earth makes missions to the planet difficult and time-consuming, but the scientific rewards are immense. Each new observation, each new mission to Neptune brings us closer to answering some of the most fundamental questions about planetary science, exoplanetary systems, and the potential for life beyond Earth. As humanity pushes further into the cosmos, Neptune will continue to be a focal point for our exploration, a reminder that even at the outermost edges of our solar system, there are still countless mysteries waiting to be uncovered. The journey to Neptune is far from over. In fact, it has only just begun. Future missions, armed with advanced technology and more precise instruments, will unlock the secrets of this distant world and its dynamic system of moons. Neptune, with its powerful storms, deep blue atmosphere, and enigmatic interior, will remain a symbol of the unknown, an invitation to continue exploring, questioning, and reaching for the stars. As we peer into the darkness of the outer solar system, Neptune stands as a beacon, guiding us forward in our quest to understand the universe and our place within it. Neptune, the distant and enigmatic ice giant at the outer edge of our solar system, represents the culmination of centuries of scientific inquiry and the boundless curiosity that drives humanity to explore the unknown. From its discovery through mathematical prediction to the fleeting yet invaluable data gathered by Voyager 2, Neptune continues to challenge and inspire. It stands as a symbol of the vast, uncharted territories of both our solar system and the universe at large. As we deepen our understanding of Neptune, we unravel fundamental mysteries of planetary formation, migration, and the dynamic forces that govern celestial bodies. Its turbulent atmosphere, shifting magnetic field, and captivating moons, especially Triton, offer a wealth of insights into the processes shaping not only our solar system, but also the countless exoplanetary systems scattered across the galaxy. Neptune's importance extends beyond its solitary beauty. It is a gateway to the Kuiper Belt, a region that holds the remnants of the early solar system, and a key to understanding the icy giants that populate other star systems. Its potential to harbor clues about the existence of subsurface oceans and the possibility of life in extreme environments makes it an essential target for future exploration. As technological advancements bring the dream of returning to Neptune closer to reality, the scientific potential of this mysterious world promises to reshape our understanding of the cosmos. In the grand narrative of space exploration, Neptune beckons us to venture further, to embrace the unknown, and to expand the limits of human knowledge. It reminds us that the quest for discovery is far from over. Neptune, with all its storms and secrets, remains a testament to the enduring drive to explore and understand our place in the universe. As we look to the future, Neptune will continue to inspire new generations of explorers, scientists, and dreamers, guiding us toward the distant horizons of the cosmos.